Hello, everyone. In this session, we will explore Newton's third laws of motion and understand the concept of the conservation of momentum. These fundamental principles are essential to understanding the dynamics of the physical world. So, let's get started. The second law of motion relates the external force on an object to its acceleration. But where does this external force come from? The answer lies in the interaction between two bodies. Let's consider a pair of bodies, A and B. Body B exerts an external force on body A. A key question: does body A, in turn, exert an external force on body B, even if they are not in contact? According to Newton, the answer is yes. The stone does exert an equal and opposite force on the Earth, but we often don't notice it due to the Earth's massive size. This fundamental idea is expressed in Newton's third law. To every action, there is always an equal and opposite reaction. Action and reaction in the third law simply mean force. Forces occur in pairs, and they are equal and opposite. It can be stated as force on body A by B is equal and opposite to the force on body B by A. There's no cause and effect relation implied in the third law. Action and reaction forces act simultaneously. Action and reaction forces act on different bodies, not the same body. They do not cancel each other out within a single body or system. Now let's explore the consequences of Newton's second and third laws. They lead to an essential concept in physics: the law of conservation of momentum. Consider a bullet fired from a gun. The force on the bullet by the gun, F, and the force on the gun by the bullet, that is, minus F, act for the same time interval, delta t. According to the second law, change in momentum, delta p equals to F delta t, where p is momentum. The change in momentum of the bullet, delta pb, is equal and opposite to the change in momentum of the gun, minus delta pg. Thus, delta pb plus delta pg equals to 0, indicating that the total momentum of the system, bullet plus gun, is conserved. In an isolated system, no external forces, mutual forces between pairs of particles can cause individual momentum changes, but they cancel out in pairs, leaving the total momentum unchanged. Thus, the total momentum of an isolated system of interacting particles is conserved. One practical application of the conservation of momentum is in the collision of two bodies. Regardless of whether it's an elastic or inelastic collision, the total initial momentum equals the total final momentum. Let's shift our focus to equilibrium. Equilibrium in mechanics occurs when the net external force on a particle is zero, meaning the particle is either at rest or in uniform motion. Forces in equilibrium must satisfy F1 equals 2 minus F2 when two forces, F1, F2, act on a particle. The vector sum of three forces, F1, F2, and F3, must be zero when three forces act on a particle. Equilibrium of three forces can be represented as the sides of a closed triangle. This principle applies to any number of forces. If sum of all forces act on a particle is zero, the particle will be in equilibrium. In summary, Newton's laws of motion and the law of conservation of momentum are foundational concepts in physics. They allow us to understand the fundamental principles governing the motion of objects in our world. I hope you've gained the basic understanding of Newton's laws of motion and conservation of momentum. As always, keep exploring, keep learning, and I'll see you in the next video.